Okay, today's topic is absorbing Markov chains. So these are the kind where you end up in a trap, right? Eventually, you're guaranteed to end up in one of these traps, right, where there's no way out. So let's just start off with a really simple example. We'll use absorbing Markov chains to study a rather simple game. It's obviously an unfair game, by the way. You've got two players, X and Y, and let's suppose that they each start off with $2. And on every round of the game, a fair six-sided die is rolled, and if a 1 or 2 comes up, X gives Y $1, and if anything else comes up, 3, 4, 5, or 6, then Y gives X $1. So this game is obviously biased in favor of X, right? X wins 2/3 of the time, 4 out of 6 times, and Y wins only 2 out of 6, or 1/3 times. That's okay. Unfair games can be just as much fun to analyze as fair games. Okay, and let's suppose that the players keep playing until one of them runs out of money. Right. So if one of them goes bankrupt, then they really can no longer play because one of them has no money to bet with anymore. Okay, so we'll model this as an absorbing Markov chain that has 5 states. A simple way to do it and easy to keep track of is we could just let states be denoted by the whole numbers 0 through 4, where the numbers represent how large X's stack of dollars are, right? or poker chips or whatever. So 0, 1, 2, 3, and 4, those are the 5 different states. State 0 is when X has nothing and Y has all $4, so Y is 1. State 4 is when X has all $4 and Y has nothing, so that's when X has 1. Of course, you've got these intermediate states 1, 2, and 3, when X has 1, 2, or 3 coins and Y has the remaining coin or coins. Okay, so here's the transition matrix for this Markov chain. Notice that we made the winning states when, let's see, when Y wins, that's when X has 0, and when X wins, that's when Y has 4. When Y wins, that's when X has 4. So those are the absorbing states. So we model those as states which always return to themselves. I mean, in the game, once you reach one of those states, really the game is over. But we can model them in the Markov chain as absorbing states. We just say that if you're in that state, you just remain there forever, right? It's kind of modeling that no further progress in the game is made at that point. And then on the other hand, you have these other states, 1, 2, and 3, where you can, sometimes you can go to an absorbing state, sometimes you can go to one of the other of these non-absorbing states. Right. Notice that again, the probabilities for the non-absorbing states, they're always either 1/3 or 2/3, because right, either Y wins if you roll a 1 or a 2, or X wins if you roll a 3, 4, 5, or 6. Okay, so this is the transition matrix here. Now, for the purposes of analyzing absorbing Markov chains, it's very convenient if you reorder the states and rewrite the transition matrix in what's called canonical form. So in canonical form, basically for our purposes, we're only going to look at relatively simple absorbing Markov chains. So canonical form can get somewhat complicated if you're dealing with really complicated types of Markov chains where you have like some groups of states that are absorbing in the sense that once you get into that group, you can't get out. And then within that group, you may have further absorbing states or subgroups. But we're not going to worry about any of that. So don't worry about what I just said. We're only going to deal with simple cases with absorbing states and non-absorbing states. And that's the only distinction we will look at. And canonical form basically just means that we put the absorbing states first. We make the absorbing states the first states, and the non-absorbing states are the remaining states. So I reordered the states here. I made state 0 and 4 the first 2, and I made states 1, 2, and 3 the last 3. right? So and when you do that, you can see why this is helpful, because when you do that, the transition matrix breaks up into a predictable form. The absorbing states, because they can only return to themselves, the absorbing states form a small identity matrix, right, in the upper left-hand corner of the transition matrix, right? Because from state 0 you can only go to state 0, from state 4 you can only go to state 4. So you've got a identity matrix up there, and then on the other hand, in the upper right, you've got all these zeros, right? You've got zeros because it's impossible if you start in state 0 or 4 to transition to any other state. So those transition probabilities are all 0. So we can say that the general scheme is that the upper half of the transition matrix, when it's in canonical form, consists of an identity matrix on the left and then zeros on the right. Now, the lower part of the transition matrix breaks up into two pieces again, but they can be almost anything. So we've got a matrix here in the lower left-hand corner over here, and those represent the probabilities of going from a non-absorbing state to an absorbing state, and that's denoted by R over here. So we'll use R to denote that section of the transition matrix. And then you've also got a section, let's see, how about, I'm running out of colors, how about pink? Okay. You've also got this section here, which represents transitions from from non-absorbing states among themselves, right? Non-absorbing to non-absorbing. And that's denoted by Q. So the transition matrix breaks up into these 4 pieces, and that's going to make it very easy to analyze the long-term behavior of the absorbing Markov chain. We'll be able to look at what happens indefinitely far into the future. Let me just make a note about the dimensions here. If M is the number of absorbing states and N is the number of non-absorbing states, then the whole P matrix, of course, is it's a square matrix of size m plus n. So it's m plus n by m plus n. The R matrix is the matrix of transitions from non-absorbing states to absorbing states, so that's an n by m matrix. And the Q matrix represents transitions among the non-absorbing states, so that's n by n. Now, some natural questions you'd like to ask about a game like this is, what's the probability of each player winning? We know that X has the advantage, right? So we know that X has a bigger than 50% chance of winning the game, but it might be nice to compute exactly what the probability is. And furthermore, we might want to know what the probabilities are with various stack sizes. Well, actually, there's only 3 different stack sizes, right? X could have $1, $2, or $3, but nevertheless, each one would have an associated probability of each player winning, and it might be interesting to calculate those. Another type of question we might ask is, on average, how long does the game last? How many rounds does the game continue, right, before one of the players gets all the money? So, and these are both questions we'll be able to answer by analyzing the absorbing, the transition matrix in canonical form. Now, one nice thing about matrix multiplication, I know it's rather weird when you first come to it, but a nice thing about matrix multiplication is that you can multiply matrices in this form here, right, in this canonical form. You can multiply them as if the entries I, 0, R, and Q, as if they were all just numbers. The logic is the same. In other words, when you multiply P by itself, you actually get 0 times 0 times R plus I times I, so you get I, and you get 0 times Q plus I times 0, which is 0, and you get, let's see, Q times R plus R times I in the lower left, and then you get Q squared plus r times 0 down here. So you can just multiply them using whatever your favorite method is for matrix multiplication, and you can multiply them in the same way and get a valid formula for the result. So p squared is going to look like this, right? It's going to break down like this, and you can see that this means that the behavior of powers of p is not too bad. It's quite manageable, as it turns out. In particular, the upper part of the matrix is invariant. It remains as I and 0, right? So that's always going to be the case. In the lower right side, what we seem to get are powers of q, and you'll see that's the same thing happens when we look at the third power of p. We get q cubed. The most complicated part is in the lower left section, and in the lower left section, initially we get this. We get r plus qr. At the third power, we get r plus qr plus q squared r, and the pattern is that each time we do it, we get one additional term that looks like a power of q times r. So the overall scheme is going to be that when we're looking at p to the kth power down here, the upper row is the same as always. It's I and 0. We've got q to the k in the lower right, and as I said, the most complicated part is this lower left entry, but that's going to be r plus qr plus q squared r plus q cubed r plus etc. until we get to the q to the k minus 1 power term. And it's a little more convenient to just factor out the r on the right. Of course, with matrix multiplication, you have to be careful to factor things out on the correct side. Since r is a right factor, we have to factor r out on the right. So it's going to be the sum of powers of q times r, right? That's what we get over here. And so in order to be able to analyze the long-term behavior of this Markov chain, we have to figure out what p to the k is going to look like as k goes to infinity. And that boils down to figuring out what q to the k looks like and what this sum, the sum of the powers of q, looks like as k goes to infinity. Okay, well, q to the k is actually quite simple. The key observation is that q is a kind of leaky transition matrix, right? It is a transition matrix in that it represents the transition probabilities from non-absorbing states to other non-absorbing states. But it's leaky in the sense that sometimes a transition occurs not to another non-absorbing state, but to an absorbing state. And those probabilities are not represented in Q, right? So if you look back, let's see, let me go back to the previous page. If you look back over here, you can see that the numbers in Q, it looks like a transition matrix, except the rows don't always add up to 1, because the numbers in Q are not always all the numbers in the row of P. So in this case, in the first row here, it's missing the 1/3, and in the third row, it's missing the 2/3. So both those rows are short, so to speak, right? They don't add up to 1. And that's what I mean by saying that Q is like a leaky transition matrix. So, there we go. So what happens when you have a leaky transition matrix is every time you raise it to a power, the leak kind of ramifies. You lose more of the probabilities, right? Every time you multiply it by that leaky row, you're going to get you're going to lose some of the values in Q, right? And the upshot is, and I'm not doing this in complete rigorous detail, but the upshot is that as k goes to infinity, q to the k approaches 0. So the whole q to the k matrix is going to approach 0 as k goes to infinity, right? So you raise a q to a high enough power, it's indistinguishable from just all zeros, right? And that just corresponds, again, to the common sense observation, that if you look far enough into the future, the probability of remaining in a non-absorbing state is virtually 0, right? Eventually, you're certain to go into an absorbing state, right? If it's even possible to go into an absorbing state, then that will happen eventually, and that corresponds to the fact that it's impossible in the long run to remain in the non-absorbing states, and therefore the probabilities in q to the kth power must be approaching 0. Okay, now here's a cute little trick. Let's take a look at this other one. This looked like the most complicated thing we were going to have to analyze, which is the powers of q, or the powers of q. Oh, incidentally, we can think of this first term I, we can think of that as like q to the 0 power. I mean, the same rule for powers works with matrices as it does with ordinary numbers. Anything to the 0 power is 1, except with matrices, it's not 1, it's the identity matrix, right? So we can think of this as like q to the I is like q to the 0 power. So basically, these are the powers of q, and we're adding them up. Well, okay, we've done this before. You've done this before, right? You've worked with the ordinary geometric series of real numbers, right? If r is a real number, 1 plus r squared plus r cubed. In fact, you've worked out the both, I think, the sum of the finite series and also the infinite series. The infinite series actually is slightly simpler. An infinite geometric series adds up to 1 over 1 minus r. So, gee, is it possible that we could use the same formula for the matrix geometric series, right? This is basically a geometric series of matrices, right? So what would the corresponding formula be? Well, of course, you can't take a reciprocal with matrices, but the reciprocal corresponds to taking the multiplicative inverse, right? And 1 minus r would correspond to I minus q, and the reciprocal would correspond to taking the inverse. So, is it possible that this infinite geometric series, so when you take the limit of this series as k goes to infinity, you get the infinite geometric series in q. Is it possible that that would really be equal to I minus q inverse? Yes, it is, and it works. And I'm going to show you maybe a slightly simplified proof of this. Let me move my page. There we go. To check that, we check, is it true that if you multiply I minus q times the infinite series, do you actually get I, right? That would prove that they're inverse matrices of one another, right? That they're inverses. Well, it's a pretty simple thing to do. If you multiply I times the geometric series, you get this. If you multiply negative q times the geometric series, you shift all the terms in the geometric series over by 1, right? The I becomes minus q, and the q becomes minus q squared, and so on. And then when you add everything up, all the q's cancel, and you're just left with I. So yeah, it works. It turns out that this infinite series over here, this guy, this infinite series is just equal to I minus q inverse. And so that's a nice simple formula we can use to compute an infinite sum of matrices, right? So that's a pretty neat trick. Now, this matrix, the geometric series in Q, I plus Q squared plus Q cubed, etc., we've just seen that it's equal to I minus Q inverse, and this is denoted by capital N, and it's called the fundamental matrix of this Markov chain, right? So it's the fundamental matrix of the absorbing Markov chain. And what we've now seen and established is that as k goes to infinity, as we look further and further into the future, p to the k approaches a simple matrix. The top is just I0, right? So all zeros in the upper right. The bottom is nr on the left and all zeros on the right. Okay? So we know what the limit is going to be now, right? And that wasn't even that hard to do. Now, this matrix nr is often denoted by A, okay? And this matrix A is actually a probability matrix, right? Which is easy to see because remember P is a probability matrix. All the rows are probability vectors. And all the powers of P are also probability matrix. All the rows are probabilities. Therefore, the limit should be a probability matrix where all the rows are probabilities. And since the lower left part is all zeros, all the probabilities must be in the nr part, right? So in fact, all the rows in nr must add up to 1. So in fact, it is a probability matrix. And that's what we denote by A. Okay, and now the significance of these entries, well, you can kind of figure it out for yourself, right? Think about what this means. The rows correspond to one of the rows in A correspond to the non-absorbing states. The columns in A correspond to the absorbing states. So the probabilities in A represent the probability that if you start in a particular non-absorbing state, that you will eventually end up in a particular absorbing state, right? So in other words, each entry Aij, the entry in A in the ith row and jth column, is the probability of ending up in the jth absorbing state given that you began in the ith non-absorbing state. Okay? And so let's work out the example of the game, right? So in our game, we had these two matrices, R and Q, right? And now what I've done here is I used Mathematica to do the calculations for me. So I entered what the Q matrix was. I computed the fundamental matrix N. Incidentally, in Mathematica, you can use the identity matrix function to give to get an identity matrix. So you just enter the size of the identity matrix. So identity matrix bracket 3, that's the size 3 identity matrix. Subtract off QMAT, and then there's also another built-in function inverse, which actually computes the inverse matrix. So here in one line, we just compute what N is, the N matrix. And right. Oh, and then I entered the R matrix and multiplied the N matrix times the R matrix to get the A matrix, and then finally, this is what you actually end up with at the end. So here's the A matrix as computed by Mathematica, and you'll notice that the calculation probably was correct because it is indeed a probability matrix. Right, each row adds up to 1. And then we can use A to calculate probabilities of any player winning from any starting state. Okay, so with our A matrix, we can now answer some specific questions about probability. So for example, as a first example, suppose we start in the first non-absorbing state. So this is the state where player X has $1, player Y has $3. And then what's the probability of finishing in the second absorbing state? Right, so we start in the first non-absorbing state. What's the probability that end up in the second absorbing state? Now remember, the second absorbing state was the state 4, where X actually wins all $4, where X actually wins all the money in the game. And if we look that up, that would be the 1-2 entry in the matrix, right? The entry in the first row, second column. It's actually 8/15. And so even though player X started at a disadvantage, X had only $1 while Y had 3, nevertheless, it's slightly more likely than not that X will win the game because the game is so biased in X's favor. Right? One more example. Suppose we start in the apparently fair state where both players have $2. So that's the second non-absorbing state where both players have $2. What's the probability the game finishes in the first absorbing state? Now the first absorbing state is state 0. That's where player X has $0, so Y has 1. Right? So if we start off with each player having $2, then the probability that Y wins, that we end up in the first absorbing state, well, to get that probability, we look up the 2-1 entry in A, and that 2-1 entry is 1/5. So even when we start out fair with each player having $2, it's rather unlikely that Y will win the game, right? Y has only a 1/5 chance of winning a game, and again, that shows the bias of the game in favor of player X. Just to make things slightly more complicated, suppose we're not sure what state we're going to start in. Suppose, for example, we're either going to start with player X having $1 or player X having $3. So we're either going to start in state 1 or state 3, and they're both equally likely, right? Kind of a weird situation, but maybe you flip a coin to determine what state you're going to start in. Okay. Under those circumstances, what's the probability that player X wins? So it's actually quite simple now. we make a state vector. A state vector is just a probability vector, a vector of probabilities, right? And it's called a state vector because it represents the probabilities of being in each one of the possible states. So the initial state of the game can be represented by this state vector, where there's a 1/2 chance of being in state 1, there's 0 chance of being in state 2, and there's also a 1/2 chance of being in state 3, right? So that represents equal probability of being in state 1 or state 3. And then what you do is you just multiply that state vector times A, right? So basically you're just adding, you're taking 1/2 times the first row of A when you start in state 1, and 1/2 times the third row of A when you start in state 3, and you add them up to get the weighted average of the two probabilities, and the result is this. So we see that if we run the game that way, we're starting from either state 1 or state 3 with equal probabilities, then there's actually a 4/15 chance that, that should be the probably Y way. Oh, I got to fix that. Okay. That we end up in the first absorbing state. Now, the first absorbing state was when X has $0, and therefore Y would win, right? So in this situation, the probability of Y winning is 4/15, and the probability of X winning is actually 11/15. I will fix that. Now, the other type of question we can answer is questions about waiting times. How long do we have to wait until the system reaches one of the absorbing states? So we answer these questions by phrasing it in terms of the number of visits the system makes to non-absorbing states. Right? If you count the number of visits to the non-absorbing states, that's the same thing as counting the waiting time until you reach an absorbing state. So okay, so to think about this, let's fix some non-absorbing state I. So I is going to be fixed throughout this calculation, and J, however, could be any of the non-absorbing states, including the same as I, right? And we'll let V sub J be a random variable representing the total number of visits to state J. And the way we'll calculate the expected value of V sub j, is by the method of indicators, which is used often in probability theory. So I think I mentioned indicators in an earlier video, but they're random variables that only take the values 0 or 1. So you could think of them as indicating whether some event has occurred or not, right? So if the value is 1, the event has occurred. If the value is 0, then the event has not occurred. And so I'm going to define a set of indicators I sub jk, which is supposed to indicate that the system is in state j at time k. Okay, so it takes the value 1 if that's true, and it takes the value 0 if that's false. Right? So for each run of the Markov chain, ijk will take a value of 0 or 1, so it's a random variable. Now, one of the nice things about indicators is that their expected value is the same as the probability of the underlying event. So the expected value of I sub jk is the same thing as the probability that the system is in state j at time k. Well, we're talking about non-absorbing states here. I and j are both non-absorbing states. So basically that's the same thing as asking what's the probability that if you start in non-absorbing state I, that you'll end up in non-absorbing state j, k steps in the future. And of course, you can calculate those by using powers of p, but we saw earlier that when you raise p to higher powers, that the non-absorbing states, the transitions among non-absorbing states, can be represented just by a power of q. So we don't even need to look at the whole p matrix, we just look at the q matrix. So in fact, this probability of being in state j at time k, given that we started in state I, is just going to be equal to the ij entry in the q to the k matrix. So I'm denoting that by q sub ij of k. Right? But works the same. You know, the notation is analogous to the notation we use for the p matrix and little p sub ij. Right? But here we're just talking about non-absorbing states, so we can just look at the q matrix. And then furthermore, the total number of visits that we make to that jth non-absorbing state, that'll just be equal to the sum of all those indicators over all times, but for the fixed j, right? So we add up I sub jk for all times k, and that gives us the total number of visits we make to state j, right, at any time in the future. Or even the starting time counts also. Okay, so summing this all up, what we've got is we can now take the expected value of the number of visits to state j. Now, expected value is always linear, so in other words, the expected value of a sum is always the sum of the expected values, so we can break v sub j up into its infinite sum, and we can write this as the sum of the expected values of the indicators, and each indicator has an expected value that corresponds to an entry in q to the k, little q sub ij of k. So what this means is we add up all these ij entries in q to the k, and that's the same thing as taking the ij entry in the sum of the q to the k matrices, right? That geometric series of q to the k. When you add up this series, you're just adding the entries in the matrix up component-wise. So you're doing the same thing as when you add these entries here. So the result is that this matrix N, the fundamental matrix of the observing Markov chain, is equal to the expected number of visits to state j, given that the system started in state I. Right? So it's a table that tells you the expected number of visits you're going to make to any particular non-absorbing state, given that you start in any particular non-absorbing state I. So as an example, suppose you start in the third non-absorbing state, and you ask, how many visits will we make to the first non-absorbing state? So we're starting in the third non-absorbing state, so we look in the third row, and we want to count the number of visits to the first non-absorbing state, so we look in the first column. So this would be the 3-1 entry in the fundamental matrix N, which is 1/5. Okay? So probably we're not going to visit it, but about 1/5 of the time we visit it once, and something like that, right? If we ask how many visits do we make to the third non-absorbing state, again, assuming that we start in the third non-absorbing state, you would expect that to be higher because, after all, we started in the third non-absorbing state, and that's going to count as one visit, right? The initial start that we made in that state counts as one visit. So, in fact, that is significantly higher, right? It's 7/5 instead of 1/5. It's over one visit higher. And if you want to calculate the total waiting time until the system reaches an absorbing state, then you just add up all the entries in one of the rows. So, for example, if we want to know the total number of visits to any non-absorbing state, given that the system starts in state I, you just add up all the entries in state I. So if I add up those three entries, I get the total number of visits to state 3, the total number of visits to any non-absorbing state, given that we started in state 3, right? So if you add those up, we get like 11/5, right? Now, to answer the question from about the game, this N here is actually this is the N matrix that I computed on Mathematica for the game, right? The die rolling game. And in the die rolling game, we start in the second non-absorbing state. So we look at the entries in the second row and add them up. So you add up N21, N22, N23, and that would represent the total number of time steps you spend in non-absorbing states before you reach an absorbing state. Now, notice that I subtracted 1 here. I subtracted 1 because we don't really count that initial state as a turn, right? The game starts in that initial state 2, where x has $2, but we don't really count that as a turn of the game. A turn of the game is when you roll the die, right? So I'm subtracting 1 off to be a little bit more precise about this. We don't really want to count that initial state as a turn of the game. Okay, so if you subtract that off, what you find is that the expected number of visits to all non-absorbing states, not including that first one, is 13/5. So that's between 2 and 3 turns. So that's how long you expect the game to last, about on an average of 2 or 3 turns. Not very long, right? And I guess that's not surprising because player X has a big advantage. So player X is quite likely to win in 2 turns, right off the bat. And very unlikely. It's not very likely to go much longer than that. Let me do one more example, and I'll do this thing all at once from start to finish, so you can see it's not really that complicated, right? You just have to do a few calculations, and use a computer by all means, right? To do the calculations, you want to compute the fundamental matrix and do all the matrix multiplication and everything. You use a computer. It's actually pretty straightforward, and doesn't even take very long to do. So here's another kind of simple example. Suppose you repeatedly roll this 6-sided die, and you keep rolling until either a 1 comes up twice in a row, or a high roll, which I define as meaning a 5 or a 6, until that comes up 3 times in a row. Right? So you keep rolling until either a 1 comes up twice in a row, or a 5 or a 6 come up 3 times in a row. Now, the probability of a 1 coming up twice in a row, if you just start rolling now, is 1/6 times 1/6 would be 1/36. Probability of a 5 or a 6 coming up is 1/3. So the probability of that happening 3 times in a row, starting now, is 1/3 times 1/3 times 1/3, about 127. So it's slightly more likely that you'll get the 5 or a 6 coming up 3 times in a row we'd expect. But we'd like to do the exact calculation. What exactly is the probability of ending up in either one of these states, right? Are we more likely to end up with 2 1s or with 3 high rolls? And what exactly are the probabilities? And how long on average do we have to roll until one of these things happens? Okay, so we model this as an absorbing Markov chain with 6 states. Now, pretty obviously, the 2 absorbing states are the 2 states where you end the process, right? So I'll denote one as 1, 1, where you end up with 2 1s in a row, and the other state where the process ends is HHH, where you end up with 3 highs in a row. So those are going to be the 2 absorbing states. If you reach either one of them, then we model those the end of the game by saying that you always return to those states in the future. Now, there are actually 4 non-absorbing states. In the non-absorbing states, you have to capture all the information you need to know about your state in order to proceed with the game, right? So at any particular point in the game, you have to keep track of, if the game isn't over yet, if procedure isn't over yet, you have to keep track of whether you've already rolled a 1, because in that case, you only have to roll 1 more 1 in order to stop. Or you have to keep track of whether you've already rolled a high roll, and if so, whether you've rolled 1 or 2 in a row already, right? So the non-absorbing states are, I'll just call it state 0, where the previous roll was neither a 1 nor a high, right? So we don't have anything going on that we can complete, right, or continue. State 1 will be the previous roll was a 1. That means we only have to roll 1 more 1 to complete the process. On the other hand, if we roll anything besides a 1, then we're back to state 0. We're back to scratch, right? We got nothing. Well, I should say if we roll a 2, a 3, or a 4, we're back to nothing. If we roll a 5, or a 6, and of course that's a high roll, and then we'll be in the state I'll call H, which means the previous roll was high, but not the roll before. So currently, we're working on 1 high roll, and if we roll another high, we'll then have 2 in a row, and that will be my last non-absorbing state, where we have 2 high rolls in a row, and in that situation, all you need is 1 more high roll in order to complete the process, right, to reach an absorbing state. So here's my transition matrix in canonical form, right? So I've done the states in the order I described over here. So this is the 1, 1 state, this is HH, and then we've got the 4 non-absorbing states here, right? 0, 1, H, double H. I think you can pretty easily work out what the probabilities are. The probabilities are always either 1/2, 1/3, 1/6, or 0, right? Because the only thing that's significant is if you roll a 1, probability 1/6, or if you roll 2, 3, or 4, probably 1/2, or if you roll a high roll, which is probability 1/3. So those are the only significant rolls, right? And then sometimes transitions are impossible. So for example, starting from state 0, where previously you've rolled neither a 1 nor a high roll, you can't get immediately to either one of the absorbing states, so that's why these two numbers are 0. Whereas if you're in state 1, then if you roll a 1 again, you'll reach the first absorbing state, so that's why this number is 1/6, right? And if you have two H's, if you're in the HH state, and you roll a high roll, then you reach the second absorbing state. And so that probability is 1/3, because there's two ways to do that, a 5 or a 6. Okay? So I'll let you verify that I've got all these probabilities filled in correctly over here. But what that gives us is the R matrix over here and the Q matrix over here. And then I would suggest that you plug these into Mathematica, or whatever your favorite math software is. And you can compute the fundamental matrix, I minus Q inverse, and we got this. And you can also then compute the A matrix, the matrix of probabilities, by taking n times R, and we get this. Always a good idea to double check, make sure that the rows in the A matrix add up to 1, and they do, so I probably did this calculation correctly, right? Okay, now to answer the questions, what are the probabilities that we end up in each of the two states? Well, the probability of ending up in state 1, the first absorbing state, that would be that would be A1, little a sub 1. In other words, we're starting in the first non-absorbing state, state 0, where we don't have any streak to build on, and we're wondering about the probability of ending up in the first absorbing state, right? So, and the probability turns out to be 13/27, right? So the probability of ending up in state 1, of rolling two 1s, is 13/27. The probability of ending up in the high state, rolling three highs in a row, is 14/27. It's just slightly more likely, right? The second question was, how long on average will the process last? So once again, I said, let's look at all the entries in the N matrix, in the first row, rather, of the N matrix, right? Those are all the number of visits we make to all the non-absorbing states, assuming that we started in the first non-absorbing state, right? And that is the starting situation where we have no streaks going on. So I added up all the entries in that row. Once again, I subtracted 1 because we don't really want to count that first state as a turn. That doesn't count as a die roll, right? The system starts in state 0 initially, but we haven't rolled any dice yet. So I'm going to subtract 1 because we don't want to count that as one die roll. So it looks like the total number of rolls, if you add up the numbers in that first row, they come out to be 53/8, so that's about 18, right? So it seems that you're going to have to roll the die about 18 times on average before this process stops.